Topic 3.3 Standard Test Methods and Interpretation. On impact test is quite different from other standard tests in that we use different type of specimen. Over here you can see a notch specimen having the dimensions of 10 by 10 by 55 millimeters, and the specimen is normally called a Sharpie specimen, and the parameters obtained from the Sharpie impact test is the absorbed energy in the unit of joule. Within the test, the standard Sharpie specimen is hit by a pendulum at the opposite side of the notch, and then the energy required to break open the specimen is measured, and it is plotted against a range of test temperatures. As this test is designed to indicate the temperature that is safe for the metal to be used at such temperatures. The picture on your right hand side here showing the schematic diagram of the Sharpie impact test machine. The sample will be secured over here on the anvil, and up here is the hammer or the pendulum that will be released to move down to impact onto the specimen. And you can imagine that the brittle materials will break open very easily, but for the tougher materials, we'll need more energy for it to break open. And once we're talking about the energy, over here is the hammer with a known weight, and once the hammer is lifted up at a certain height, it will possess the potential energy equal to mgh. And once the hammer is released, this potential energy is transformed into the kinetic energy while moving down here to hit on the specimen. And to break open the specimen, some portion of energy is used for the plastic deformation and fracture to give new crack surfaces. But not all the energy is used up. The rest of the energy left will move forward the hammer to swing into the opposite side. And you can see that the further the hammer swings to the opposite side, the more brittle the material is. And by recording the energy absorption during breaking up, we can plot the values against the test temperature, as you can see in this picture. The metals having BCC crystal structure will change its fracture behavior from ductile to brittle when experiencing a change of temperatures from high temperature to low temperature. And that is because of the nature of the operating slip system, which are sensitive to temperature. After performing the test, we can plot the data to obtain the ductile to brittle transition temperature curve, or the DBTT curve, as we can see over here. And you can see that the absorbed energy in the unit of joule is on the y-axis, whereas the test temperature is along the x-axis. And the test temperature range is designed to identify what range of temperature that the materials can be used without possibilities of brittle failure. As you can see from here now that the absorbed energy is plotted against the temperature, as you can see from the curve here. And its shape looking like the S-curve or the 10th curve. So on the line in the middle here showing the transition temperature. And you can see that to the left of the transition temperature, the metal absorbs very low energy during fracture. And this is because BCC crystal metals, although having many slips, but they are not ready to operate at such low temperatures like this. However, as the temperature increases, that will allow more slipping to operate at higher temperature, and therefore the BCC metal can experience more plastic deformation before failure, and then absorb more energy. And once the temperature increases to a certain level, more and more energy is absorbed during fracture, and that is when the metal behave or fail in the ductile manner. And for engineers, we have to identify the temperature that is safe for the metal to be used in service condition. It is conservative criterion that should be used at the temperature that it can absorb the most energy, which is up here on the upper shelf of the curve. So therefore, we can also divide the curve into three regions. One that is on the upper shelf, one that is in the middle here is called the transition range, and one down here that is called the lower shelf, where we have to avoid using the metals in this temperature range. So from the impact test, the obtained parameters is the absorbed energy. And remember that the greater the absorbed energy, the higher the impact toughness of the metal. And if we're talking a bit more detail about the energy absorption, over here I'm giving you the example of the break open sample tested under low temperature range. Up here is the notch, and the rest of section bear the load during impact of the pendulum. And you can see at low temperature, the cross-section of the specimen is very square. That means no plastic deformation involved into the fracture process. And once we investigate the fracture surface SEM, we can see very flat surface over here that signifies very few energy absorbed during fracture. On the other hand, if you're looking at the sample that break open at high temperature that is felt on the upper shell at higher temperature, you can see that more plastic deformation going on along the side of specimen here. And when we investigate under the SEM, we can see a rougher surface, 100% dimples, giving very high surface area, and that will require high energy for the fracture process. So from the Chapter impact test, we have to plot the absorbed energy against the temperature to identify the transition temperature to tell that what temperature is suitable for service condition. And also, if we could investigate the fracture surfaces, that will give us more idea what caused the failure. And as I mentioned earlier, that only the BCC metals that experience the ductile to brittle transition behavior, and that is due to the limited active slip planes operating at low temperature, and that will give less chance for the metal to deform in the plastic manner, and then showing less plastic deformation, and then subject to brittle failure at low temperatures. Give you again the ductile to brittle transition temperature curve on the red line here. And this curve is showing the ductile to brittle transition of the low-strength BCC metals, such as low-carbon steels, for example. You see looking like the S-curve, where the transition temperature is over here, and the upper shelf is right there. The increasing temperature allows more slip system to operate, and therefore yielding more plastic deformation in this case. And if we compare to other metals having different crystal structures like FCC or HCP, those metals do not experience ductile to brittle transition, and therefore they give the same energy absorption at any temperatures, so you don't have to worry about what range of temperature you have to be careful about. For the FCC metals, there are plenty slip system operating at all temperatures. That's why the absorbed energy is not sensitive to test temperature. But for other high-strength alloys, as you can see from the green curves here, the absorbed energy is not sensitive to the temperature, but some might absorb less energy in service, so we have to be careful, because they might have high strength but with limited ductility, and that will result in lower toughness, unfortunately. Now here I would like to give you the case study first on the Titanic tragedy. And this happened long ago, and people in your age might have heard about the Titanic movie. And the tragedy happened in 1912 when the British largest ocean liner, with a size of 250 meter long and 32 meter high, it was in service at the time, and it was estimated that more than 2,000 people on board. Sadly, it sank in the early morning of the 15th April 1912 in the North Atlantic Ocean when she collided with an iceberg at around almost midnight during her maiden voyage from Southampton to New York City. So by looking at the picture, it's quite sad, isn't it? And lower down here is the picture showing the sketch of Titanic. And before the tragedy happened, she looked very beautiful in the ocean. It was found out that the transition temperature of the steels used for the ship structure was higher than the steels that we use nowadays. And that is because of the technology for the iron and steel making that made the steels that we use nowadays cleaner, stronger, and tougher. From the picture on your right hand side here, there are 3 different ductile to brittle transition temperature curves. The lower ones here are for the Titanic, tested in the longitudinal and transverse direction if we compare to the normal steel. We can see that at the freezing temperature, while Titanic was sinking, over here, at zero temperature, you can see that almost zero energy can be absorbed during fracture, while the impact energy of the steel that we use nowadays is much higher. An investigation of the fracture surface under SEM later showed that the flat fracture surface with manganese sulfide was found as crack initiation, like you see over here. And another picture here shows the evidence of manganese sulfide within the microstructure. So nowadays, the steels that we use having less inclusions like one of the manganese sulfide. Then the steel is tougher and strong and safe to be used in a wider range of temperature. So it is important to know that if the transition temperature is high, that means the curve is moving to the right. It is not safe for use at low temperature. But if the whole transition curve moving to the left, it means that the transition temperature or even the upper shelf can be reached at lower temperature, and it is now safer to use at such temperature. So we need tougher materials for safety reasons. That is to require high energy absorption for the metal to be used at service temperature. The next case study is the Liberty ship, as you can see from the picture on your right hand side. And if you look carefully, you can notice a huge crack over here. So for this case, 7 of the Liberty ships built during the World War II broken completely in two as a result of brittle fracture. And over 1,000 of approximately 5,000 merchant ships built during the World War II had developed cracks of considerable size by 1946. And this was very challenging for engineers in those days without knowing what happened. And then the investigation took place to understand the cause of the failure. It was found that it is the crack that initiated from the defect in the welded area, and with the temperature that is below the freezing temperature, similar to the Titanic case. And therefore, there are 3 basic factors that contribute to a brittle cleavage fracture. First is the triaxial state of stress. Second is the low temperature. And third is the high strain rate. It is not necessary to have all 3 factors altogether. Just 2 of the 3 factors can produce brittle environment to the BCC metals, and to the greater extent of these 3 factors, the more serious that the brittle fracture will take place. To explain a little more here on the triaxial state of stress, is the state of stress found on the defects such as cracks. And that's why when we produce the metallic components, we have to make sure that there are less and less defects within the structure of the processing. And the quality assurance is necessary now. Another factor is low temperature, and that is you can clearly see by looking at the test data. Very low temperature towards the sub-zero temperature is not as good for the BCC metals. And the last one is for the high strain rate. It's showing the speed of the force applied onto the samples. And the impact test simulates the fastest speed of testing when the pendulum is delayed to quickly hit onto the sample. So the higher the strain rate, the more the metal is subject to brittle failure. This is another case study that happened on the river bridge. It is a collapse of the Milnes River Bridge in Connecticut, and it is thought to be due to improper maintenance, material corrosion, poor design of pin and hanger technique, for example. And by looking at the picture, you wouldn't want yourself to be on the bridge at that time. And one thing I want you to keep in mind that when the failures happened, we do have to investigate the cause of failure so that we can prevent it from happening again, that we can avoid the destruction and also people's lives. And it is not the fault of the bridge itself or the materials it used to construct the bridge. It is us as the engineer who designed to use the material as the first place, who is responsible for the maintenance of the whole thing. So think about it. Another case study is from our country, the collapse of Ayutthaya River Bridge, like you see in the picture here. Not so much different, isn't it? So we can avoid this to happen, and it's up to us to do so, to prevent before failure due to occur. And now we come to the summaries of the chapter, mechanical properties and testing. We have gone along 5 different standard tests, which are tensile, hardness, fatigue, creep, and impact tests. So for now, shall we try for the selection of mechanical tests for particular applications? First, on the gear teeth. The gear teeth is subject to wear and thermal in service, and therefore the most suitable mechanical test would be the hardness test. And for the next example is the piston valve that is subject to thermal, wear, and also cyclic loading. And therefore, the suitable mechanical test would be hardness and fatigue. Next is the suspension bridge that I'm giving as the example many times. It is subject to tension, torsion, and cyclic loading, and therefore the suitable mechanical test would be tensile test, torsion, and also fatigue test. And the next one is the solar thermal power station that is subject to tension, thermal, also oxidation, and cyclic loading. Therefore, the mechanical test that would be applied is the tensile test, creep, fatigue, and torsion. And the last one here, the nuclear power plant that is subject to tension, thermal, along with oxidation, cyclic loading, and also impact. And therefore, tensile test, creep, fatigue, and impact test. So I hope that at the end you get the idea of the principle and the interpretation of the standard mechanical test